Hello and welcome to this lecture. We're going to continue our look at connections between linear equations and linear transformations. That's what we are doing with more examples. So the examples here are going to be slightly more involved and there will be more cases coming up. So let's look at this one. The example we're going to see, which is the third example in our series, has 4 variables and 3 equations. Okay, so here is the equation. So you see 4 variables I'm calling as x, y, z and w, and you have some coefficients, you have some RST on the right hand side. You know that the right hand side is sort of plays a role, but later on. So what we are more interested in is the matrix corresponding to this linear transformation, which is represented by this matrix, right? So 1, 1, 1, 1, 2, 2, 1, 3, 4, 1, 4, 5. Okay. Once you have a linear transformation represented by a matrix, you have to worry about its null space and column space. So let's do that. To find the column space, we know we have to look at the RREF of A transpose, and if you look at A transpose becomes a 4 by 3 matrix, right? What is A transpose here? It will be 1, 1, 1 in the first row, 1, 2, 2 in the second row, 1, 3, 4 in the third row, 1, 4, 5 in the fourth row. So it becomes a column, a longer sort of vertical thing here. And then if you do RREF, it turns out you will get 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, etc. Okay. So the column space of A, column space of A, which is obtained through the RREF on A transpose. I was sort of explaining why the columns have to become row for you to do RREF easily, right? So that is the span of 1, 0, 0, 0, 1, 0, 0, 0, 1, and that ends up being R3. Okay, so dimension 3. Okay, so this is the first thing we have figured out the column space of A. What about null space? Null space, we know we have to do RREF of A, and we do RREF of A, and from here also we know the nullity is 1, isn't it? So for this matrix A, number of columns is 4, dimension is 3, rank is 3, means nullity is 1. Okay, we know that, fundamental theorem tells you that. But if you do RREF of A also, you get nullity 1. You notice here there's one free variable, and that one free variable can be set equal to 1, and you solve for the other dependent variables, you get a basis for the null space. So that way you can see that the null space is 1, right? The free variable was set as 1. Free variable was set as 1, and then the dependent variables were computed as -1, -1 and +1. Okay, so you notice null space as dimension 1. So I figured out the range, I figured out the null. Now I can start drawing my linear transformation pictures. So how does the input space get transformed to the output space by a linear transformation represented by A? Let's look at that. Here is our sort of asymmetrical tabla mridangam type picture showing up here. Here's the matrix. I know my range, I know my null. Notice here the couple of interesting things here. Now my transformation T is from R4 to R3. Okay, notice that I'm showing R4 with a bigger ellipse, just to say it's a larger space, and then R3 is sort of maybe a smaller dimension space that's here. And what happens when you go from T, when you transform with T, which is represented by this matrix A, right? My range is the entire R3, which means the entire R4 is going to go to the entire R3. Okay, so that's the picture, and I've shown that through this yellowish, orangish color shaded here. Okay. Now notice, interestingly, the null is not a single point in this particular case. Null is also a one-dimensional guy, 1, -1, -1, 1 u, and that is shown here. Okay. So all the points in this null go to the 0 here, right? That we know. So there is a reduction in the dimension. From a one-dimensional object here, it's going off to 0. Okay, so there ends up being a reduction in dimension. So in this type of thinking in terms of dimensions and transformations and null is very strongly linear algebraic thinking. Okay, so you have to develop some of those ideas here. We always think in terms of dimensions. I mean, every variable is a new dimension type thing, right? So you have 4 variables here, starting 4 variables, but after this transformation, you have only 3, right? So transformation sort of kills one of the dimensions. The null space ends up going to 0. Okay. So now let's start thinking about how the solutions can be, right? So how can the solutions be? So you pick an RHS, any RHS you pick, it will be in the range, right? You can never ever pick a right hand side which is not in the range. Why? Because the range is the entire R3 and your right hand side is only the R3. So you're going to pick any point that will be in the RHS. So once you have RST, it means there has to be a solution, it is in the range, so there has to be some vector which transforms to this. So you can go ahead and solve it, right? So how do we do it? We're going to solve this equation. We're going to do elimination, solve it. If you do that, you will get something like this. Okay, so notice there will be one free variable after you eliminate, and the w variable you have to set to be equal to u, and then write it back here and then solve it, and then you can split it as a constant vector plus something into u, and no wonder this null space shows up here as well. So like I mentioned, the null space always shows up in the solution of a linear equation. You can't avoid it. Okay, so that's nice to see. So you have infinitely many solutions for every point in the RHS. Any point you pick in the RHS, because the range is the entire R3. The entire R3 is caught up there. So these kind of mappings are called onto mappings. Many to one, but everything in the range is covered. So everything in the codomain set is covered. So that is the range. Okay, so hopefully you're getting a feel for what we are doing here. There is a linear equation. The linear equation has an underlying linear transformation, and we're going to sort of picture the linear transformation in an abstract sense using these tabla pictures where you go from one space to the other. There is a null, there is a range. Depending on where your RHS is, you may get different types of solutions. In this particular case, you're getting infinite solutions for any RHS. Okay, so next example. Example 4 is a little bit more twisted. We're going to now look at 3 variables and 4 equations. Okay, so you have 3 variables and 4 equations. So your matrix A now is a 4 by 3 matrix. I'm going through very quickly here. You do RREF on A transpose to find a nice basis for the column space. You're going to get 1 0 minus 1 minus 2 and 0 1 2 3. So your dimension becomes 2. So it's a rank 2 matrix. Same way, if you do RREF on A, you get again, you notice that the nullity is 1, the rank is 2 here, and you get nullity of 1. Okay, rank 2 is nullity 1, right? Fundamental theorem of algebra tells you there are 3 columns here, rank is 2, nullity will be 1. And again, you solve for the basis vector here, you put a 1 for the free variable, you get minus 2, 1. Okay, so null space is dimension 1. I figured out a null space, I figured out my range. So now I can start visualizing the linear transformation. So let's do that. So any equation of this form with 4 variables, 4 coordinates in the right hand side, right? There are 4 coordinates in the right hand side. Now, so my T now is a 4 by 3 matrix, which means it is a transformation from R3 to R4. Okay, so it takes a vector of length 3 and transforms it into a vector of length 4. Can you see that? So if you take A and multiply on the right by a column vector of length 3, you're going to get a column vector of length 4. So that's what this means. This T is transforming a vector from R3 to R4, but interestingly, R4 is really, really big, right? So it's got like a crazy mridangam type shape now. It's not even a proper thing now, right? It's gotten very, very asymmetric. R4 is a big guy here, and then R3 is smaller. And notice what my T is doing. It's taking R3 itself to an even smaller dimension space. It's taking R3 to a 2-dimensional space, right? Not even 3-dimension. Dimensions are not preserved. There is a non-trivial null here, which is 1-dimensional, which will go off to 0. So 1 dimension is getting killed further. Okay, so R3, instead of ambitiously trying to go into R4, which anyway it cannot, it's not even keeping up as R3. It's losing 1 dimension by this transformation T. Okay, so this is my range here, and this is my null here, and this is the picture here. So once you have this picture, you can start thinking about what will happen if the RHS is inside the range, outside the range, etc., etc. Okay, the first easy solution is if you have the RHS outside, then there is no solution. The next case is if it's inside. Okay, if it's inside, what will happen? See, if you see a point in the range, if you say Q and R here, you're going to get Q, R, and then 2R minus Q, and then 3R minus 2Q, right? So if you multiply this with Q and this with R, so you will get that form. So if you put that form here and solve it, you will get a solution. You will get, in fact, infinitely many solutions. We know that, right? So I don't have to do that, So I know if I put a point in this range here and I solve, I'm going to get infinitely many solutions. The null is going to show up there. I'm going to get a solution. That's going to happen, right? I mean, just by practice, we haven't proven this. We'll prove it later on that these kind of things will happen. Okay, so I know from inside the range, I will go to infinitely many solutions. Okay, so a lot of things are happening, different types of equations based on the range and the null and the dimensions. You have different types of solutions depending on where the right hand side lands up. Okay, so all this calls for more careful study. You know, I mean, how do you push to the general case? In the general case, when you have m equations and n variables, what are all the various things that can happen? Let's see that next. Okay, so how does the general case look like? Okay, the general case would look something like this. You have an equation Ax equals b. It's a very famous equation in linear algebra. So you have these equations. X1 to xn are my variables. I'll call it as a vector x. B1 to Bm are my right hand side values. I'll call it as a variable, a vector b. And the matrix A has these coefficients A11, A12, A1n, and then there are m rows, and this is how it looks. So one thing to remember is the shape of this matrix can vary depending on m and n. I've just shown it as one generic form. It may happen that m is greater than n, in which case it will be a tall matrix. It may happen that m is less than n, or n is much larger, in case it will be a very long, horizontally long matrix. And then it could be square also. M could be equal to n. It could be square. So all these you have to keep in mind, except that I'm just showing it generically here. So this equation, we know sort of this linear transformation controls the solutions of these equations. Okay. So first thing to do is to start with column and null spaces, and what we do there is exactly the same, right? So the same type of calculations with the RREF you have to do with A transpose. You will get a rank R, and you will write down column space as a span of R vectors in Rm, right? So notice here the column space belongs to Rm, right? M dimensional, the span of the columns, and you're going to do the RREF to figure out a easy basis vector for that span. Okay, so you get these R vectors. Okay, so for the null space, I'm going to do RREF on A. Later on, we'll see some examples, but anyway, nevertheless, RREF on A. The nullity is going to be n minus r, right? So rank is r, n is the number of columns, so nullity is n minus r by the fundamental theorem, and the null space will be a span of n minus r vectors in Rn, and from the RREF we can find these n minus r vectors. So you can take your take the free variables and put them as coordinate the canonical basis and solve for the dependent variables and get these things. So I'll show you some examples going along. Okay, so this is the first step to do. Once you do this, you understand the column space and the null space, you can start visualizing the linear transformation and think about what may happen. Okay, so so we saw some curious, interesting things, right? So for instance, we saw that the null space always showed up in the solution of a linear equation. Okay, why is that? Okay, and we were getting bogged down by the calculations and elimination and all of that. One of the promises of such abstract studies of linear transformations is you need not be bogged down by routine calculations. You can see it from a high level and sort of prove similar things. Okay, so I'm going to show you one such proof. It's very interesting and simple, but nevertheless, I hope you find it fascinating in terms of how this abstract theory gives you a very nice feel for how actual answers will end up being. Okay. Okay. So here is a linear transformation view of the solving process. What do we do when we solve the linear equation? What are we doing exactly? So here is the equation Ax equals b, and I'm going to say a linear transformation T from Rn to Rm is represented by this A is an m cross n matrix. So what is the solution? Given a vector v in Rm, okay, in Rm, I have to find all the u in Rn which satisfy this. Under T, T of u should become v. Okay, this is what I'm looking for. When I'm solved, this is what I'm looking for. Okay, so let's analyze this a little bit more abstractly. So the starting point is something interesting. So I'm going to assume something. I'm going to assume by some crazy guess or some clever method or something, I found one solution. Okay, somehow I found one solution to this equation, T of u equals v. I found a u naught such that T of u naught is v. Don't ask me how, for that you need some techniques, but let's say you find it. If there is one solution, see, it may turn out that you can never ever find a solution. I showed you some examples, right? If your right hand side, if your v is not in the range, then you won't get any solution, right? So that can also happen. So if I know that the v is in the range, I should be able to find one. So let's say I find one. Once I find one, here is a little trick here. Notice what's happening here. You consider any other vector which is in the null of T. It's in the null of t, which means what? T of w is 0. And then what you do, you look at what happens to u naught plus w. You take any vector in the null of t and look at u naught plus w. Because t is linear, t of u naught plus w is going to become t of u naught plus t of w, right? But what is t of w? 0. What is t of u naught? V. Okay. So, notice what is going on. Once I have one solution, any vector in the null space will give me another solution, because t of u naught plus w is also v. Okay. So, this little idea is a very simple abstract idea, but nevertheless it gives you this understanding of why is it that the null space shows up in the solution of a linear equation, right? You have one solution, you add a null vector to it, you get another solution for the linear equation. It's very easy to argue. All null vectors do ax equals 0, right? So, if you have a ax equals b solution, and if you add a null vector to it, you should continue to get the correct solution, right? So, that is what is going on here. So, u naught plus w is the solution for all w in null t. Okay, so this one people write a little bit differently. So, what happens is, you use this notation, you say the set of all u naught plus w where w belongs to null t, this is like set theoretic notation here, hopefully you understand. You take the same u naught, the one solution you somehow found, add all the null space vectors to it. So, you will get a whole space, no? That I am going to call it as u naught plus null of t. Okay. So, this is my sort of abstract notation for it. So, these are all solutions for the same equation t of u equals v, right. So, in fact, what is interesting is that this is the set of all solutions. There can be no other solution outside of this set. There is a little proof you can do here. I am going to skip that. I am not doing it in this class, but nevertheless, I hope you find this connection between the null of the linear transform and the solution of the linear equation is sort of direct and simple. Okay, so the simple little connection is there between solving a linear equation and finding the null of a linear transformation. Okay, so this is the reason why null shows up all the time. Okay, so I think this is a good point to maybe take a break in this lecture. We'll come back and do some examples and actual ways of solving these equations in some manner. Thank you very much.